Welcome back to AI Paper Podcast. Today we're looking at self-refining video sampling from a team at KAIST, NYU, and DeepAuto.ai. So if you just need the 60-second version for your stand-up meeting, here it is. We all know models like WAN 2.1 or Cosmos. They look amazing, but they're physically clueless.
Totally. They hallucinate objects, bend things that should be solid.
Exactly. They just ignore Newton's laws. And the usual fix is, really expensive retraining or super slow rejection sampling.
Yeah, generate 100 to get one good one.
This paper introduces Predict-and-Perturb. It's a training-free method that basically treats flow-matching models like denoising autoencoders. It makes the model refine its own latents.
How does it do that?
By predicting the clean video and then adding noise back in, but at the same noise level inside the sampling loop.
It's like a little self-correction cycle.
Yes. And it pulls the video back onto the data manifold, fixing things like floating objects or limbs that just disappear. The stats are wild over 70% human preference and a huge jump in robotic grasping success, all with zero fine-tuning.
It's basically finding the physics engine that's already buried inside the model. You just have to change how you sample.
Okay, that's the short version. Let's really get into it because this paper is, it's tackling one of the most annoying problems in generative video right now. If you've played with Sora or WAN, any of them.
Yeah.
You know the dream logic problem.
Right. Dream logic is the perfect phrase for it. These models are incredible at synthesizing textures. They know what a cat's fur looks like, how light should reflect off a floor.
Oh, flawlessly.
But they don't have a core understanding of object permanence or rigidity.
The paper points this out right away. They've got this example of a gymnast on a pommel horse. And the default generation, it looks photorealistic, but then suddenly the gymnast just sprouts a third arm to keep his balance.
Or his leg just phases right through the horse.
Also ghosts, yeah.
And that's a classic manifold issue. The model is like drifting off the manifold to what's physically possible. It's optimizing for texture, for looking good, but it loses the structural constraints.
The constraint that, humans generally have two arms.
Exactly.
I also love the sand example. You have a prompt about kids playing with sand, and in the baseline model, the sand just starts moving on its own.
Telekinetic sand.
It's telekinetic sand.
Yeah, that's a failure of causality.
Eh.
The model learned that sand pits involve moving sand, sure. But it didn't encode the causal link, that the sand should only move if a hand or a shovel actually touches it. So it just animates everything.
So as an ML engineer, if you want to fix this, let's say for a robotics simulator, you're kind of stuck, right? You can do rejection sampling, which is what? Generate 100 clips and just throw 99 of them away.
Exactly. You run the prompt 100 times, maybe slap a pose detector or some physics verifier on top, and you keep the one that doesn't look completely broken.
It works, technically, but it's just wildly inefficient. You can't run a real-time robot on a strategy that needs 100 failures for every one success.
No way. And the other option is fine-tuning.
The brute force approach.
Right. You build this massive data set of physically accurate simulations, maybe from Unity or Unreal, and you just hammer the model with examples of gravity and collision.
But that's so expensive, and you risk catastrophic forgetting, right? Where the model learns physics but forgets how to make things look real.
Yes. So this paper comes along and says, hold on, you don't need to retrain. The model already knows the physics. You're rushing it.
That's the whole idea. And they introduced this self-refining video sampling, which uses an algorithm they call Predict-and-Perturb, or PMP.
I do like the name.
Predict-and-Perturb. It sounds like a terrible management strategy, but here it's a sampling loop. So walk us through this. They're reinterpreting flow matching.
They are. Most of these modern video models use flow matching. You can kind of picture it as a straight line from a block of pure noise to a final clean video. The sampler just solves an ODE to walk along that line.
So it takes a step, denoise a little, takes another step, denoises a little more. It's a one-way street.
It usually is, yeah. It never looks back. So if it makes a mistake at, say, step 5, like it starts drawing on third arm, it just spends the rest of the generation refining that mistake.
Making a very photorealistic third arm.
Precisely. But what these authors realized is that the flow matching objective is mathematically equivalent to training a time-conditioned denoising autoencoder, a DAE.
DAEs, that's old school. That's like deep learning from 2014.
It is, but the concept is solid. A DAE is trained to take corrupted data and predict the clean original. So at any point in the generation, any time step t, the model is technically able to guess at the final clean video Z1.
So even if you're only halfway through, the model has a rough idea of what the final output should be.
It does. And that's the key to the PMP loop. You're at some step T. First, you ask the model to predict the final clean video, Z1. That's the predict step. But, and this is the clever part, instead of moving forward, you take that predicted clean video and you add noise back into it.
You corrupted again.
Yes. But crucially, you add just enough noise to get it back to the same noise level you were just at. You're not moving forward in time. You're staying put at step T.
Okay, so I'm trying to picture this. It's almost like I'm sculpting with clay. I use a tool to smooth it out, that's the prediction, but then I see a flaw, so I slap some wet clay back on.
That's the perturbation.
Right, and I try smoothing it out again, all before the clay actually dries.
That's a perfect analogy. You're refining the shape before it sets. In the math, you're performing this stochastic refinement that pulls the latent representation back toward the data manifold.
The data manifold being like the zone of high probability realistic videos.
Correct. A video where a cup just floats in the air is a super low probability event. It's way off the manifold. By cycling this predict-and-perturb loop, you let the model's own internal priors kick in. The model knows cups are supposed to fall. So each loop, it just nudges the cup down a bit, closer to a valid physical state.
And they do this a few times at the same time step.
Yeah, maybe 5 or 10 times per step. And they found it's most effective really early in the generation, like when MBAT is less than 0.2.
Which makes sense. That's when all the course structure is being decided, the what goes where. You fix the physics then, and the textures can just follow along.
Exactly. If you wait until the end, the concrete is already set. You can't move the arm anymore. You can only change the lighting on it.
Okay, so reading the paper, it seems like if you just apply this loop blindly, you hit a pretty nasty problem. They call it over-refinement.
Oh, yeah. This is where the engineering reality bites back.
Mm-hmm.
If you just loop PMP over and over, you get what the internet calls a deep-fried image.
Deep fried. So like super high contrast, oversaturated colors, just crunchy.
Exactly. And the culprit here is usually classifier-free guidance, or CFG. We use CFG to force the model to stick to the prompt. It boosts the signal. But if you're applying CFG repeatedly inside this loop,
You're just amplifying that signal again and again at the same step.
it's like shouting the same instruction louder and louder. And the result is that the static parts of the image, like a plain wall in the background, start to look really weird. The texture gets grainy, the colors shift. The background doesn't need any physics fixing, but it's getting hammered by the guidance anyway.
So they needed a way to apply PMP only to the things that are moving or are physically interacting and just leave the background alone. But they can't use an external object detector. That would defeat the whole purpose of being training free and fast.
And this is my favorite part of the paper. They came up with uncertainty-aware PMP. They figured out a way to make the model basically report its own uncertainty.
How does a model tell you it's uncertain?
They compare the model's prediction of the clean video between two back-to-back PMP loops. So you look at the prediction from loop 1 and the prediction from loop 2. For the background, the wall or the floor, the model's super confident. The prediction barely changes at all between loops. But for the gymnast's moving arm or the falling sand, the model is struggling. It's trying to figure out exactly where each pixel should be. So the difference between the prediction at loop 1 and loop 2 is high.
So high variance between loops equals high uncertainty. And that correlates perfectly with motion.
Perfectly. They use that difference to generate what they call an uncertainty map. It's basically a heat map for movement. Then they just apply a binary mask.
Yeah.
If uncertainty is high because it's moving, apply the PMP refinement. If uncertainty is low, it's a static wall, just freeze it, do nothing.
That is incredibly clever. It fixes the deep fried problem because you stop over-processing the background.
And it solves the efficiency problem. You don't need another neural net to find the objects. You're already calculating those predictions in the loop, so creating the mask is mathematically free. It costs 0 extra NFE neural function evaluations.
Okay, so they have a method to fix physics and a way to stop it from wrecking the image quality. Let's talk results, because if this actually works, it's a huge deal for anyone building with generative video.
The results are very, very strong. They tested on WAN 2.1, WAN 2.2, and Cosmos. They used a benchmark called Dynamic Bench, which is designed specifically to test complex human motions.
That's where the gymnast example comes from.
Right. And in human evaluations, so just people watching videos side by side and picking the better one, the PMP method had a 73% win rate over the default sampler.
73% is not a small gain. This is obviously better kind of number.
It's a landslide. But for me, the PAI bench results were even more compelling. That's the robotics benchmark.
Right, embodied AI, using video generation to actually plan robot actions.
The task is image to video. You give the model an image of a robot arm and a bowl, and the prompt is pick up the bowl. If the generator hallucinates the bowl teleporting, well, the robot fails.
Or if the gripper closes, but the bowl just stays there.
Right. They found that default Cosmos and One models fail at this a lot, and they just hallucinate the interaction. With PNP, they improved the grasp success rate by about 11% on Cosmos and 8% on One 2.2.
An 11% jump in success without training on a single new robot video. That's wild.
It's effectively turning a creative model into a more scientific one, and it outperformed a best-of-4 rejection sampling baseline. So generating one video with PNP was better than generating 4 videos with the base model and picking the best one.
That's a massive efficiency win. What about just raw physics, like gravity?
They used a couple of benchmarks, Firewall bench and Pisa bench, to simulate free fall. You know how in old cartoons a character runs off a cliff and just kind of hangs there for a second before falling?
Yeah, the Wile E. Coyote physics.
Default video models do that all the time. Objects float or they fall in these weird, unnatural curves. PNP made those trajectories much, much tighter. They actually measured the L2 distance against ground truth gravity sims, and the PNP videos were way closer to real-world physics.
So it basically decartooned the generation.
It forced the model to listen to the gravity priors it had already learned during pre-training, but that it was ignoring during the normal, faster sampling process.
The paper also had a section on spatial consistency. This is that classic 360-degree camera pan problem.
Ugh, yes. The bane of anyone doing architectural visualization. You pan the camera around a room, and by the time you get back to where you started, the sofa has changed color or the window has moved.
The room just reconfigures itself behind your back?
And PNP showed much higher consistency there. The reason goes back to that mode-seeking behavior we talked about. A room that stays consistent is a high probability state. A room that morphs is low probability. By constantly refining the latent back towards the mode, PNP essentially locks the geometry in place.
It stops that hallucination drift, but to be fair, it didn't fix everything. There's a really interesting failure case with mazes.
Yeah, the maze test. This is a super important negative result. They gave the model a top-down view of a maze and just asked it to generate a solution path. PNP gave 0 improvement.
Why not? If it can fix a gymnast's arm, why can't it find its way out of a maze?
Because PNP is a local optimizer. It looks at the image and asks, does this look physically plausible and texturally correct right now? It doesn't have a global planning module. It can't understand the logic of start here and there and don't cross any lines.
So it can make sure the line it's drawing looks like a good line, but it has no idea if that line is the correct solution to the maze.
Exactly. It refines execution, not strategy. If the base model has 0 clue about maze logic, refining its output won't magically give it that logic.
That's a really crucial distinction. It unlocks dormant knowledge. It doesn't create new knowledge.
Perfectly said.
I want to quickly position this against other tools people might have heard of, like Freenet. We've seen Freenet used to stabilize videos. How is this different?
Freenet is great, but it works on the initial noise on Z0. It's trying to find a better starting block of noise that will lead to a good video. PNP works on the intermediate steps on ZT.
So Freenet is about the plan, and PNP is about steering during the journey.
That's a good way to put it. And Freenet can be expensive because you often have to run the whole generation just to see if your starting noise was good. PNP is correcting the trajectory in real time, step by step. It's much more targeted.
And what about something like SD-Edit, where you take an image, add noise, and then denoise it to make a change?
SD-Edit is more of a global hammer. If you use it on a video frame, you often change the semantic content. The person's face might change. The layout of the room shifts. PNP is different because it relies on cross-frame consistency. It's using the model's own prediction of the same video to refine itself.
Ah, so it keeps the who and where, but it fixes the how.
Yes. It maintains the semantic fidelity while improving the physical fidelity.
So zooming out, we have a paper that's basically saying our current video models are actually way smarter than they look. They're not broken, they're just rushing the exam.
And if we give them this little sanity check loop, this predict-and-perturb mechanism, they can correct themselves. They can fix their own floating objects and warping limbs without us having to spend millions on retraining.
And it's model agnostic. That, for me, is the killer feature. You can take this technique and just apply it to One or Cosmos or whatever model comes out next week.
It's a plug-and-play inference trick.
Yeah.
And it moves us a pretty big step closer to having video models that can actually serve as reliable world simulators.
Well, so here's the thought I want to leave you with.
Yeah.
The paper mentions that video is naturally more robust to this kind of perturbation than a single image because of temporal consistency. You have the previous frames to ground you.
Right.
If we can use this kind of self-refinement to fix physics, could we eventually use it to debug a model's understanding of causality in real time? I mean, imagine a system that doesn't just generate a video, but actively fights its own hallucinations to discover physical laws it didn't even know it knew.
That is the big question, isn't it? Are we building video generators, or are we accidentally building physics engines that are just buried under all this noise and need to be dug out?
A hallucination machine that corrects itself into a physics engine. I love that idea.
It's a fascinating time to be watching this space, that's for sure.
It really is. Thank you for listening to this episode of AI Paper Podcasts. As always, the link to self-refining video sampling is in the description. You should check out the uncertainty maps. They're actually really cool to look at.
Yeah, definitely worth a look.
We'll catch you on the next one.